In this question, we're given a function f, which is a function of x and y, namely x cubed minus 12xy plus 8y cubed, and we're asked to find and classify the critical points of f. So to find the critical points of f, what we would like to do is take the partial derivatives and set them equal to 0. So let's get started on that. The partial derivative of f with respect to x is 3x squared minus 12y, and the partial derivative with respect to y is 24y squared minus 12x. Now to find where these critical points happen, what we want to do is set the partial derivatives equal to 0. So the first equation I'll get is by setting the partial derivative with respect to x equal to 0. And so we get 3x squared minus 12y is equal to 0. And the second equation, let's just clean that up a little bit. 3x squared minus 12y is equal to 0. The second equation that I get is by setting the partial derivative of f with respect to y equal to 0. So we get 24y squared minus 12x is equal to 0. Of course, I can simplify this equation if I just divide both sides by 3. So I have x squared minus 4y is equal to 0. And this one I can simplify by dividing both sides by 12. So I get 2y squared minus x is equal to 0. Okay, so let's go about solving these two equations for the two unknowns x and y. So from equation 2, I see that if I rearrange that, I get x is equal to 2y squared. So now wherever I see an x, I can plug in instead 2y squared. So I go up to equation 1 here, and I can plug in 2y squared wherever I see an x. So into equation 1, I get 2y squared, that's x squared, because in equation 1 x is squared, minus 4y is equal to 0. So what this means is 4y to the fourth minus 4y is equal to 0. Of course, I could divide both sides by 4, and I get y to the fourth minus y is equal to 0. And I can factor out a y out of both of these terms, and I'm left with y cubed minus 1 is equal to 0, which leaves me with two cases. Either y is equal to 0, or y cubed minus 1 is equal to 0. Those are the only two cases I can possibly have. Okay, so case 1. In case 1, let's just assume that y is equal to 0. Okay, if y is equal to 0, then we can actually go back up and we can plug that back into, let's call this equation 5, or not equation 5, let's call this equation 3. Put that into equation 3, and we end up with x is equal to 2 times 0 squared, which is 0. So if we let y be 0, the result is x equals 0, and so one critical point is 0, 0. Okay, case 2. That's the case where y cubed minus 1 was equal to 0. Case 2. Y cubed minus 1 equals 0. Of course, I can rearrange that and make it y cubed is equal to 1, which means the cube root of 1 is, of course, equal to 1. So that gives me y equals 1. Now, if we plug that into equation 3 again, into 3, what I end up with is, plug that back into equation 3, y is equal to 1, I get x is equal to 2 times 1 squared. So x is equal to 2 times 1 squared, which of course is just equal to 2. So another critical point is the point x equals 2, y equals 1. Okay, so those are our critical points, but the next thing that they would like us to do is classify the critical points. So in order to classify the critical points, we are going to need the second derivatives. So let's go ahead and calculate the second derivatives from the first derivatives here. fxx is the derivative of f sub x, so the derivative of this with respect to x. So if I actually take this derivative with respect to x, I get 6x. fxy, which is the derivative of this with respect to y, I get negative 12. And fyy is the derivative of this with respect to y, and I get 48y. So let's go ahead and calculate D for each of these critical points. So for critical point 1, which was 0, 0, we have that fxx at 0, 0 is equal to, so D is equal to, for 0, 0, D is equal to fxx at 0, 0 times fyy at 0, 0 minus fxy at 0, 0 squared. So let's take a look at what all these partial derivatives are. Fxx is 6x, and of course when x equals 0, that means fxx is 0, so this becomes 0. Fyy at 0, 0. Fyy at 0, 0, when we plug in y equals 0, gives us 0 again, so that's 0 times 0. Fxy at 0, 0, well, fxy is negative 12 no matter what the point is, so this becomes negative 12 squared. This becomes negative 12 squared. So D in this case for the point 0, 0 ends up being 0 minus 144, which is negative. And whenever D is negative, this means that 0, 0 is a saddle point. Carrying out the exact same calculation for the point 2, 1. So D for the point 2, 1, for the point 2, 1, we get that D is equal to fxx at 2, 1 times fyy at 2, 1 minus fxy at 2, 1 squared, and that's equal to fxx at 2, 1, while x is equal to 2, so that's 12. So we can put in 12 here, times fyy at 2, 1. So let's take a look at fyy. When y is equal to 1, that's 48. So 12 times 48 minus fxy at 2, 1. So fxy is always negative 12, no matter what the point is. So this becomes negative or minus negative 12 squared. And if you actually calculate this out, what you'll find is 12 times 48 is clearly bigger than 12 times 12. So 12 times 48 minus 12 times 12 is going to be a positive number. And we also notice that fxx at 2, 1 is a positive number. So fxx at 2, 1 is a positive number. So because D is a positive number and fxx is a positive number, that leads us to conclude that 2, 1 is a minimum. And that's that.